Hello everyone, welcome to Earth Archives. Today we are going to explore one of the most mysterious forces in the universe, gravity. Have you ever wondered why objects fall? Why don't we float in the air, but are instead constantly drawn towards the Earth? How does this powerful force affect everything around us, and even the entire universe? We will start from history and gradually uncover the mysteries of gravity. What is gravity? In the vast universe, there is a mysterious and powerful force, gravity. It is invisible and colorless, yet it can control everything. You experience its presence every day, whether you're standing, walking, or dropping something from your hands. So what exactly is gravity? How does it affect our world? And why is it so important? Let's start with the simplest things in our daily lives. Have you ever noticed that when you drop something, it always falls down? This is gravity in action. Every object on Earth is attracted by Earth's gravity, causing everything to move toward the center of the Earth. This phenomenon is commonly known as weight, and this force is generated by Earth's mass. So, why is this invisible force so powerful? The answer lies in the mass of an object. You can imagine Earth as a giant magnet, and because it has a huge mass, it generates such strong gravity. This is why the gravity we experience on Earth is so strong that we can't escape its pull. In fact, it is because of Earth's gravity that we are able to stand firmly on the ground and live and reproduce on this planet. But gravity is not just limited to Earth. Our sun, other planets, stars, galaxies, and even the entire universe are all influenced by gravity. When we look up at the night sky and see the shining stars, they are not just floating randomly in space. They are being pulled by the gravity of surrounding celestial bodies. Just like Earth orbits the sun, every planet, moon, and even dust in the solar system moves under the influence of gravity. Now let's talk about the fascinating nature of gravity. You may have heard of Einstein's theory of relativity, which offers a new understanding of gravity. In this theory, Einstein tells us that gravity is not just a force of attraction, but a curvature of space and time. He describes that when a large mass like the sun exists, it causes the surrounding space and time to curve. This curvature makes other celestial bodies follow a curved path, just like objects rolling on a curved sheet, always moving toward the lowest point. This new perspective completely overturns our traditional understanding of gravity and helps us better comprehend some of the fascinating phenomena in the universe. For example, why can a black hole consume everything, including light? It's because the gravitational pull of a black hole is so strong that it can distort the surrounding space and time, trapping all matter and light in its grasp. From Galileo to Newton, the discovery of gravity. In the distant past, humanity's understanding of the world was not as profound as it is today. The sky and the earth were shrouded in mystery and the unknown for most people. It wasn't until an Italian scientist, Galileo Galilei, with his insatiable thirst for knowledge, began exploring the phenomenon of gravity that the journey of human understanding of gravity began. Galileo's story is like an inspiring adventure that takes us into a time full of curiosity and wisdom. By the late 16th century, Galileo had already started studying the motion of objects. He had heard many different theories about how objects fall. Some believed that heavier objects fell faster, while others thought all objects fell at the same rate. However, Galileo was not satisfied with these rumors and decided to use scientific methods to solve the puzzle. He dropped objects of different weights from the Leaning Tower of Pisa and discovered that, regardless of their weight, the objects fell at nearly the same speed. This finding overturned the traditional beliefs of the time. He concluded that the speed at which an object falls is not related to its weight, and this theory laid the groundwork for later studies of gravity. However, Galileo's discovery was just the beginning. He did not completely solve the mystery of gravity. It wasn't until the late 17th century that another brilliant British scientist, Isaac Newton, came onto the scene and took Galileo's observations to their peak. Newton's story is also full of wonder. On a quiet afternoon, while sitting under an apple tree, an apple suddenly fell, and this ordinary sight led him to ponder the nature of gravity. Why did the apple fall to the ground instead of floating up to the sky? This question led Newton to deep thought and eventually led to his discovery of the law of universal gravitation. Newton's theory of universal gravitation explained not only why the apple fell from the tree, but also how planets orbit the sun. He proposed that every object in the universe exerts an attractive force on every other object, and this force increases with the mass of the objects and decreases with the distance between them. This theory completely changed humanity's understanding of the laws governing the universe and became the cornerstone for later scientists in the study of celestial motion and physical phenomena. Newton's Philosophiae Naturalis Principia Mathematica formally presented his law of universal gravitation. This groundbreaking discovery not only rewrote the history of physics, but also laid a solid foundation for the scientific developments that followed. From Galileo's simple experiments to Newton's profound insights, the journey of discovering gravity was like a long trek to explore human intelligence, with each step revealing the endless mysteries of the universe. The mysterious properties of gravity. Newton discovered the basic laws of universal gravitation, but it still carries many mysteries. Compared to the other three fundamental forces, strong nuclear force, electromagnetic force, and weak nuclear force, gravity has many differences. 1. Gravity is very weak. In our daily lives, gravity is always present with every movement we make, whether objects fall or people walk on the ground. We can feel its force. However, in the realm of deep physics, gravity is actually a relatively weak force, especially when compared to the other three fundamental forces, which make gravity seem quite insignificant. These three forces are the strong nuclear force, electromagnetic force, and weak nuclear force, each with a much greater range and intensity than gravity. Let's take a closer look at the differences between these forces. First, the strong nuclear force is the most powerful force in nature, acting between protons and neutrons inside atomic nuclei. Its strength is about 1 trillion times greater than gravity, or even more. The range of the strong nuclear force is very small and usually only operates within the atomic nucleus, meaning it does not affect the motion of objects in our daily lives. However, this force plays a crucial role in the stability of atomic structures, preventing atomic nuclei from disintegrating due to the repulsive electromagnetic force between protons. Therefore, although the strong nuclear force is not apparent in the macroscopic world, it is the foundation for maintaining the structure of matter. Next, the electromagnetic force is responsible for interactions between electric charges. The range of the electromagnetic force is much larger than that of the strong nuclear force. Its strength is approximately 10^36 times greater than gravity, which means that, although we don't directly feel its effects in daily life, it is everywhere. From electricity to magnetic fields, from the movement of electrons and atoms to friction between everyday objects, all of these are closely related to the electromagnetic force. The electromagnetic force is the fundamental cause of various chemical reactions in matter and is the basis of modern technological development. Whether it's the computers and phones we use or the lights that illuminate the night sky, the underlying operating principles all rely on the support of the electromagnetic force. Then, the weak nuclear force plays a very special role in particle physics. While its strength is weaker than the strong nuclear force, it is still much stronger than gravity. The weak nuclear force is mainly responsible for certain particle transformations within atomic nuclei, such as in the process of radioactive decay, where unstable atomic nuclei release electrons or other particles. And this is where the weak nuclear force comes into play. Its strength is about 10^25 times stronger than gravity, and it plays a critical role at very small scales, although we cannot directly feel its effects. In contrast, the strength of gravity is incredibly weak. Gravity only acts on objects with mass, and its strength is directly proportional to the mass of the objects. For example, Earth's gravity allows us to stand firmly on the ground, but this force is much weaker compared to the other three fundamental forces. While gravity certainly has a far-reaching impact in daily life, it cannot have a significant effect on microscopic or atomic structures. Despite this, gravity plays an irreplaceable role at the cosmic scale, as it governs the movements of galaxies, planets, and other celestial bodies. Gravity is a one-way attractive force. In our daily lives, gravity seems to be the most ordinary force, constantly influencing us. From our walking to objects falling, everything is under its control. Imagine, when you open your eyes in the morning and stand up, you immediately feel a powerful force pulling you firmly toward the ground. That is Earth's gravity. This invisible force seems to have a one-way attraction characteristic. It always pulls objects toward the center of the Earth, and this phenomenon is a mystery that scientists have long tried to understand. The one-way attraction of gravity is not a simple intuitive fact. Its mystery lies in the fact that it only pulls objects toward the center of the Earth and does not act in reverse. Think about it. If you throw an object into the air, no matter how high it goes, it will eventually be pulled back by Earth's gravity. This phenomenon has never changed. It is not because objects cannot move upward, but because this attraction is an irreversible process. When an object moves away from the Earth, it is fighting against gravity. But in the end, gravity wins, and the object is forced back to the ground. Since Galileo's experiments, humans have begun to explore gravity. By observing the free-fall motion of objects from different heights, Galileo discovered the law of accelerated falling, which laid the foundation for Newton's later work. Newton proposed the theory of universal gravitation, which is a comprehensive explanation stating that every object attracts one another, and this attraction is one way. Earth's mass creates a gravitational pull on surrounding objects, and this attraction continues to exist no matter how far objects are from the ground. However, why does gravity insist on one-way attraction? The answer is that the mass of an object determines its gravitational range and strength. Earth's mass is far greater than that of a small stone, so the stone is pulled back by Earth's strong gravity, while the Earth is not pulled toward the stone. This force is not all-powerful, but it has limits. It always pulls objects toward the center, which also explains why all objects on Earth's surface, no matter how high you throw them, will eventually fall back down. Einstein's theory of relativity, unveiling the true nature of gravity. Einstein's theory of relativity is undoubtedly one of the greatest breakthroughs in the history of physics. When we talk about gravity, we often think of Newton's law of universal gravitation, which is the first theory of gravity we learned. However, Einstein's theory of relativity took our understanding of gravity to a whole new level, allowing us to re-examine this ubiquitous natural force. Einstein's general theory of relativity not only explained how gravity works, but also fundamentally changed our understanding of spacetime. Gravity is no longer seen as a force as described by Newton, but as a phenomenon caused by the curvature of spacetime. This perspective, though difficult to accept at the time, has gradually become clearer as scientific development has progressed. Einstein's general theory of relativity tells us that celestial bodies are not attracting other objects due to some invisible force, but because their mass bends the surrounding spacetime. It is like placing a heavy object on a stretchable fabric, causing the fabric to sag downward. Other objects placed on the fabric will then move along this curved path. Although this analogy is simple, it effectively helps us understand the true nature of gravity. In other words, the Earth attracts objects not because of a visible force between the Earth and the object, but because the Earth's mass bends the surrounding spacetime, causing objects to fall along this curved path in spacetime. The revolutionary aspect of this view lies not only in how it changed our understanding of gravity, but also in how it successfully explained many phenomena that Newton's theory could not account for. One example is the precession of Mercury's orbit. Mercury's orbit exhibits a very subtle shift over time, which Newton's law of universal gravitation could not explain accurately. However, Einstein's theory of relativity was able to precisely predict the precession of Mercury's orbit and explain the underlying cause. This was a major success for general relativity, proving that Einstein's new understanding of gravity was correct. Additionally, Einstein's theory predicted that light would bend in strong gravitational fields. This prediction was confirmed during the 1919 solar eclipse observations, when scientists discovered that light from distant stars indeed bent as it passed near the sun. This phenomenon could not be explained by Newton's theory, but it perfectly matched Einstein's predictions. This discovery not only provided strong evidence for relativity, but also changed the way humanity understands the universe. Black holes and light's mystery. Einstein's theory of gravity provides answers. Black holes, these mysterious and fascinating cosmic objects, have long captured the attention of scientists and astronomy enthusiasts. Their name may sound like something out of science fiction, but their existence has been confirmed by modern science. So, why are black holes so mysterious? What is their connection to light? The answers to these questions are all tied to Einstein's general theory of relativity, a theory that revolutionized our understanding of gravity, space-time, and the laws governing the universe, and it has helped unveil the mysteries of black holes. The formation of black holes is closely related to Einstein's general theory of relativity. According to relativity, the mass of celestial bodies influences the surrounding space-time. It is like placing a heavy object on a stretchable fabric, causing the fabric to sink, and objects nearby will move along the path of this depression. When a massive star exhausts its fuel and collapses, it compresses all its mass into an extremely small space, creating a celestial body with an extremely dense mass. The gravitational pull of this body becomes so strong that it distorts the surrounding spacetime, making it impossible for even light to escape. This is the origin of black holes, a region with an extremely high mass and severe curvature of spacetime. Light, being the fastest thing in the universe, should theoretically be able to overcome any obstacle and travel across the cosmos. However, Einstein's theory tells us that when light comes close to a black hole, it is heavily influenced by gravity and may even fail to escape. This is because the black hole's gravitational field is so intense that light cannot surpass this gravitational range. Einstein predicted that when an object crosses the event horizon of a black hole, its boundary, the object's motion would appear to slow down dramatically from the perspective of an external observer, and it would seem to come to a stop. This means that once light crosses the event horizon, it can never return to the outside world, becoming part of the black hole. For decades, scientists have sought to confirm this theory. In 2019, the Event Horizon Telescope (EHT) team successfully captured the first ever image of a black hole, marking a groundbreaking discovery that confirmed Einstein's relativistic predictions were correct. In the image, we see a black hole's shadow surrounded by light radiation, which is emitted from the material that has been warped and heated by the black hole's intense gravity. This image provides us with a glimpse of the true nature of this enigmatic object. Moreover, Einstein's theory also predicted properties of black holes, such as their rotation, mass, and charge, offering further clues for study. When a black hole rotates, its surrounding spacetime is also stretched and twisted, a phenomenon known as the gravitational lensing effect. This allows us to observe changes in the light from distant celestial objects as it passes near a black hole, further verifying Einstein's theory. The discovery of gravitational waves, the vibrations of spacetime. Gravitational waves, a concept that might sound like something from a science fiction movie, are actually a real phenomenon based on Einstein's theory of general relativity. According to general relativity, the mass of celestial bodies affects the surrounding structure of spacetime, much like a heavy object placed on an elastic fabric causes the fabric to sink. When massive objects in the universe move or undergo dramatic changes, these movements cause ripples in spacetime, known as gravitational waves. However, this theory remained unproven for over a century, until 2015, when scientists finally captured the first real evidence of these waves. This discovery was undoubtedly a monumental breakthrough in the field of physics. The discovery of gravitational waves marked a significant step forward in our understanding of the universe. As early as when Einstein proposed his theory of relativity, scientists predicted the existence of gravitational waves. However, because these waves are extremely weak and only occur in extreme conditions, they could not be detected for a long time. The speed at which gravitational waves travel is the same as the speed of light, and the distortions they cause in space are so minuscule that they are nearly undetectable. Imagine that when a massive star or black hole collides, the space-time in the universe spreads out like ripples on the surface of water. These ripples subtly affect our universe, causing slight changes in the structure of space and time. However, these tiny changes are very difficult for us to detect because their amplitude is so small that even objects around us cannot perceive them. Yet, scientists did not give up. They developed specialized detection equipment, the Laser Interferometer Gravitational Wave Observatory, LIGO, to capture these faint waves. In 2015, LIGO successfully detected gravitational wave signals generated by the merger of two black holes. This discovery was a groundbreaking shock to the scientific community, confirming that Einstein's theory was correct and that we could observe these subtle yet profound phenomena in the universe. This discovery was not only a theoretical confirmation, but also opened a new chapter in astronomy. The detection of gravitational waves allows us to study cosmic phenomena that were previously inaccessible, such as black holes and supernovae. The movements, mergers, and deaths of these extreme celestial bodies generate strong gravitational waves, which carry information about the universe's deepest mysteries. Through gravitational waves, we can hear the sound of black hole collisions, something optical telescopes cannot achieve. Moreover, the discovery of gravitational waves has provided us with a whole new way to observe the universe. Traditional astronomical observations primarily rely on light waves, but light waves can only travel so far, limited by cosmic dust and other obstacles. Gravitational waves, however, can pass through all forms of matter, making them a new tool for observing the deepest structures of the universe. With gravitational waves, scientists may be able to unlock the mysteries of the early universe and even explore the inner structures of black holes. The unification of quantum mechanics and gravity. Quantum mechanics and gravity, the two cornerstones of physics, govern the microscopic and macroscopic worlds, respectively. Quantum mechanics explores how particles behave at the smallest scales, revealing the most fundamental laws of the material world, while gravity describes how celestial bodies interact within the universe. Despite both being indispensable parts of modern physics, their theoretical foundations are vastly different. Quantum mechanics is filled with uncertainty and probability, while gravity, especially as described by Einstein's general relativity, is a continuous, deterministic mathematical structure. This fundamental difference makes the unification of the two particularly challenging. Therefore, how to unify quantum mechanics and gravity into a complete theory has long been a goal pursued by physicists. The core idea of quantum mechanics is that the most basic units of matter and energy are not continuous, but exist in discrete quanta. In other words, the properties and energy of particles are not continuous, but exist in discrete, minimal units. These particles can exist in multiple states simultaneously, and their behavior is described by probability. This idea is far removed from the theories of Newton and Einstein, which assumed that the motion of celestial bodies is deterministic and predictable. However, when we attempt to apply quantum mechanics to describe gravity, significant challenges arise. In general relativity, the gravitational field is the curvature of spacetime, while quantum mechanics views particles as existing in a wave-like form, following the principle of quantum superposition. These two descriptions are mathematically incompatible because quantum mechanics involves probability waves and uncertainty, while gravity is a continuous, deterministic curvature. This dilemma has led many physicists to search for a new theory, quantum gravity. The goal of quantum gravity is to unify quantum mechanics and gravity and to explain physical phenomena at all scales. To achieve this, scientists have proposed several different models, with the most famous being string theory and quantum gravity theories. String theory suggests that the fundamental particles in the universe are not zero-dimensional points, but are like strings. The vibrational patterns of these strings determine the properties of particles. String theory proposes the possibility of unifying the four fundamental forces, including gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Such a unified theory could explain the behavior of gravity at the quantum scale. However, despite the new perspectives that string theory and quantum gravity theories offer for the unification of gravity and quantum mechanics, these theories still face many unsolved mysteries. Currently, there is very limited experimental evidence for these theories, and their mathematical structures are extremely complex, causing many physicists to remain cautious about their feasibility. Future gravity research, exploring the unknown of the universe. As technology advances, the study of gravity continues to unravel more mysteries. In the future, we may be able to solve the puzzle of unifying gravity with quantum mechanics through more experiments and observations. Perhaps one day we could actively control gravity and engage in interstellar travel, just like the advanced civilizations in science fiction, bending space-time to travel across vast distances. In conclusion, gravity is not only an essential force in our daily lives, but it also shapes the structure of the universe, determining the formation and evolution of galaxies. It is key to our understanding of the origin and fate of the universe. Thank you for watching. If you have any questions about gravity or Einstein's general theory of relativity, feel free to leave a comment and join the discussion. Don't forget to subscribe to our channel. In the future, we will continue bringing you more fascinating scientific discoveries.